Good morning, good evening, good afternoon, everybody. Welcome to the MechE Alliance seminar series. My name is Brian Anthony, along with Teresa Worth. Will be our hosts for today. The seminar series is our opportunity to engage with our students, with our faculty, with our postdocs, and our external partners to see the breadth and depth of the work that's happening at MIT. Joining us today, Kavin Kowsari has graciously agreed to give his talk on scalable visible light additive biofabrication. Kavin is a postdoctoral fellow in Professor Fang's Nanophotonics and 3D manufacturing group, conducts research at MIT and also at Brigham and Women's Hospital. He's pursuing novel research in bioprinting, hybrid bioprinting, for on-demand creation of engineered tissues for and with embedded vascularization. Dr. Kowsari did his PhD in Toronto and has a postdoctoral fellowship for his work at MIT. Kavin, I thank you very much for your time, and attendees. Please hold your questions to the end. You can send them in chat or raise your hand, and I'll marshal them to Kavin's direction at the very end. And with that, Kavin, I'll turn it over to you. Thank you for your time and attendance today, and you can share your screen and take it away. Thank you.
Perfect. Thank you so much. Let me just quickly share my screen. Okay. A very good afternoon to everyone. Thank you very much for your time and attendance. As Brian mentioned, my name is Kavin Kowsari. I'm a postdoc fellow in Professor Nick Fang's group in MechE. And I'd also like to acknowledge Professor Yu and Professor Key. And the title of my talk is Scalable Visible Light Additive Biomanufacturing. And I'm going to start with a background on my current research landscape. Then I'll get into a bit of a critical review of some of the challenges in additive manufacturing as well as biofabrication. And then I'll get into a bit of my recent work that is relevant to the area. And I'll finish off with the ongoing or prospective efforts relating to neural tissue biofabrication. So the way that I envision my research landscape is represented by the structure as shown here. So we've got the base and pillars, and these basically support some of the grand challenges or the unmet needs in different areas. For example, performance gaps in digital manufacturing, biofabrication, electrochemical energy storage devices or batteries, or improved metamaterials or biomedical devices. And the way that I view this is that foundational to this is the platform development. So this is typically the core novelty of impactful recent work. And so we want to be able to precisely position in three-dimensional space various types of advanced materials at high resolution. We want to have capabilities in terms of multi-material and multi-scale as well. And so one of the pillars is functional materials that need to be high performance and also easy to fabricate in 3D using 3D printing. And we want them to be tunable. Another pillar is process modeling and optimization that could be a good use to the system. So bringing all these elements together, it creates an environment for informed creativity. Additive manufacturing, or AM, as an enabling technology, follows roughly the following flow to come up with next generation solutions. So we typically start with modeling and design. We use high performance computing, multi-physics modeling, or topology optimization to come up with structures that are not possible to fabricate using conventional manufacturing methods like molding and casting or subtractive manufacturing. And then we move on to the synthesis of the materials. So we want to create tunable materials that are often nano-architectured, and these could be smart materials as well, or in many cases, hydrogels. So the next step is additive manufacturing, in other words, the process. So we create customized processes typically that have improved capabilities that are not present in, for example, commercial systems. And the last step is really more towards mass production. It involves qualification and certification of the additively manufactured parts. So again, all these elements together enables us to create high performance materials, components, as well as devices. And some of the ongoing or future focus areas of additive manufacturing include scaling up the size, the throughput, in other words, the speed and the resolution of the system, and also development of new and novel materials. And we also want to increase the flexibility in the submicron and the nanoscale fabrication. And we want to implement directly into the system in situ characterization or feedback control. And we also want tools for accelerated certification of these parts. So on this emerging technology hype cycle chart, we can see that consumer 3D printing or enterprise 3D printing are both past the peak of inflated expectations or the hype, and they're on their way through the trough of disillusionment onwards to the plateau of productivity. However, bioprinting, in other words, the 3D printing of biomaterials or tissues, is still relatively at its infancy. And just a few years ago, it was all the way at the left bottom corner of this plot. So what is this hype that bioprinting faces? Well, bioprinting envisions a future that involves cyborg-like humans, where we can walk around and shop for limbs or organs, and we could repair ourselves and extend our lives. But more urgently, there's an urgent need for donor organ shortage. So currently, the transplant lists clearly outweigh the available organ donors. So there are many different potential contributions of biofabrication. This could include regenerative medicine, creation of new and novel medical devices. It could be useful in disease modeling, drug discovery, and also computer-brain interface. So one of the goals or primary aims of biofabrication is to create more accurate tissue models or microenvironments. And for example, one of the biggest causes of failure in drug trials is efficacy. And that is due to the mismatch between traditional cell culture or even animal testing methods compared to the actual physiology of the human body. So if we could come up with tools that create more accurate tissue models, then we can not only improve our chances of success, but also reduce costs. And bioprinting involves or requires a team of integrated with a wide range of background in terms of their expertise. So there's the biofabrication side, which involves platform development, and it's more of an engineering problem. We've got the tissue engineering team and biomaterials, as well as other technologies like organ on a chip or that use microfluidics-based systems. So why do we want to pursue bioprinting anyway? Well, bioprinting as a tool, it allows us to replicate the geometrical repeating tissue units that we find in different organs. For example, we've got the hexagonal liver lobules or the kidney nephrons. And so bioprinting allows us to arrange or pattern these different types of cells and extracellular matrix materials in precise locations in 3D space. So it is really an enabling technology. And it involves various scales. So we start at the atomic scale, where we can modify the chemical structure of the hydrogels or the backbone of these polymers. And the fabrication typically takes place at the micro scale. and then we will create organs that have macro applications. And just a word on the evolution or progress of tissue engineering. So more common or traditional approaches include the scaffold-based method, where we have porous scaffolds that are made of bioresorbable materials. Or alternatively, there's the modular approach, where we assemble cell aggregations or sheets in different orientations or ways to create engineered tissue. And bioprinting is really an upgrade on traditional 2D or three-dimensional cell culture methods. So it allows us to create tissue that is maturable, and it paves the way towards creating suturable, implantable organs. One of the important aspects in bioprinting is harnessing photochemical reactions. So just by using light, we could induce microstructural changes in these polymeric materials. One example is isomerization or bond forming reactions, which is what we're going to focus on here. This is also called the chain growth photopolymerization. And we also have the bond breaking reactions, and this could be useful for example, drug release or controlled release of biological cues or growth factors. So we typically start with a liquid bioink precursor that contains biocompatible monomers. These could be either derived naturally or synthetically. And to this concoction, we mix in cells and other cues. And then we expose this liquid to light. And this could be in the form of either visible or near UV ultraviolet light. And this forms a photocross-linked network that is hydrophilic. And so if we've done our job right, if we've created the right environment, then the cells will behave as though they are in native tissue. So they could communicate, they could exchange nutrients, and proliferate and become functional. There are several modalities of bioprinting that have been used or adapted thus far. For example, we have the droplet-based method, which is similar to the inkjet method. And we also more commonly see the use of the extrusion-based technique, as shown in this video, using a nozzle. And we also have the stereolithography-based printing, which, in other words, it's light-based. And so each technique has its pros and cons, and perhaps we will benefit most by using or developing a hybrid process. Some of the critical focus areas of bioprinting include increasing the cell density. So currently, we're a few orders of magnitude below the therapeutic threshold for solid organs. And so that's one area. Another important area is embedding of multiscale vasculature directly into the biofabricated tissue. And this enables us to create tissues that are thicker than about 500 microns or 0.5 millimeter. And below this, we are restricted to diffusive transport of oxygen and nutrients. So to create functional thick tissue, we need multiscale vasculature. Another area is the trade-off between fabrication, ease of fabrication, and ease of cell culture. So the stiffer or more cross-linked these polymeric materials are, the easier they are to fabricate. However, cells like neural cells, they prefer ultra-low stiffness hydrogels in order to proliferate. So this necessitates the development of novel methods that can foster the growth of these types of sensitive cells. So just a bit more on embedded vasculature. This figure on top compares different techniques in terms of their ability to create multiscale vasculature. And we can see that light-assisted or light-based printing really is favorable to deliver the required performance. However, many of the light-based methods that have already been used, for example, the DLP method, digital light processing based, or laser SLA or stereolithography, these are restricted to near UV or even UV light, and that could be damaging to the cell's DNA. So potentially visible light could be an improved alternative, and which could increase cell viability and function. And another word on these light-based methods, it is difficult to create tissue that involves many different kinds of materials, many different large number of materials, and that is needed to create these tissues. So I'll get into a bit of some of the recent work that I've done. Here we created a multi-material DLP, or digital light processing based stereolithography apparatus. And this was built in-house, and it's modular. It's relatively low cost and high resolution. So the voxel size in this case was just 5 microns, but this could be reduced to even submicron. So essentially we have these resin or photopolymer puddles that could be hydrogel precursors and can contain cells. And we deliver these to the printing platform where we can expose a high resolution digital mask and selectively cross-link the material. And so in a way that each layer has more than one material. So the steps in multi-material fabrication include first projecting the portion of the image pertaining to the first material, and then undergoing an automated material exchange process and refilling the puddles, and then repeating for subsequent materials. And one of the nice things about this system is that there's a wide range of materials that we can synthesize and test, which makes it useful for different kinds of research. Here we see a time-lapse video of the process. You could see the resin puddles being refilled. And the process allows us to create these high-resolution lattice-like structures that are made of, in this case, 2 materials, but potentially more. And these could be used for different applications. For example, we could create composites or functionally graded structures. And more interestingly, we could use them to create improved lithium-ion batteries that with increased surface area. So perhaps by coating them with a nanoporous coating, we could maximize the energy density. Or in this case, we also demonstrated by capitalizing on the multi-material capability, we created pneumatically actuated micro grippers. In this case, we used 2 different materials as fibers, one being stiffer than the other, and we could control the deformation by changing the geometry. We could see in this SEM that the material transition is quite sharp, and this kind of stereolithographic based printing is very useful for the creation of hollow geometries without the need for support materials. So we created different kinds of actuation like helical or bending, and these could find applications in various kinds of micro devices. However, one of the major limitations of this technique is the restriction in the maximum part size. So we're currently limited to about less than 15 millimeters wide, and this is at this resolution. So to address this, in one of the works of our, one of the previous works of our group, together with collaborators at Lawrence Livermore National Lab, they integrated scanning optics into the DLP technique to be able to create structures that were, for example, in this case, 5 centimeters wide. Meanwhile, they contained hierarchical structures all the way down to the nanoscale. So this multi-scale capability allowed them to create mechanical metamaterials. In other words, these fall in the ultra low stiffness regime. However, they're also, ultra low density regime. However, they're extremely stiff. So in this Ashby material property chart, they're addressing some of the white space. So we also created many different kinds of or families of materials In this case, we created a highly stretchable PEG-DA acrylamide-based hydrogel for DLP-based fabrication. And for this, we had to synthesize an efficient water-soluble photoinitiator. And so we could create structures that can find applications for bioprinting, since these are biocompatible, wearable electronics using ionic conductivity. These could be used for contact lenses or even bioadhesives. And these materials are also biodegradable, so the rate could also be controlled. We could also create or synthesize shape memory polymers or SMPs that enables 4D printing. In other words, we could programmably cause deformations in these structures based on the environmental stimuli, for example, temperature, humidity, or pH value. And again, this opens up doors to create 4D grippers or shape memory medical stents and so on. And there's a lot we could do with the chemistry when we're synthesizing these materials. So instead of the permanent covalent networks found in typical photopolymers, we could utilize dynamic bonds that are able to click and unclick. And to some degree, this allows us reshapeability or repairability of the parts, and also recycling. So we could use these materials in different applications. And all of this is without much compromising the mechanical performance. And following a similar path, we could impart self-healing in these materials or controlled degradation. So this is a demonstration of the modularity of the system. In this case, we integrated into the system acoustic particle patterning using PZT ultrasonic transducers. This is done with our collaborators. And so by exciting these transducers at their resonant frequencies, we could arrange particles or microspheres or fibers in prescribed patterns that are highly predictable using finite element modeling. So this allows us to arrange these fibers at the individual layer level, and we can create reinforced composites or bio-inspired anisotropic materials that are found in nature. But very importantly, this is also used for cell patterning. These acoustic waves or surface acoustic waves are typically used in cell sorting applications. So, yeah. So more recently, I began to better suit the DLP system towards bioprinting. And I started to think about ways that we could address the major limitations of DLP printing. And these limitations are lack of scalability, as well as use of UV light. So I proposed adopting active matrix organic LED or AMOLED microdisplays as the digital light modulator that emits visible light. So here is a low-cost proof of concept system that I put together, and it's high resolution, as we can see on this performance chart. It's high throughput. In other words, we're a couple of orders of magnitude above DLP technologies, and meanwhile, we're still high resolution. So the voxel size is still on the order of some types of cells. And of course, visible light is benign to cells versus UV-based systems. And interestingly, we also have reduced scattering of the light compared to ultraviolet light. And this is because of the longer wavelength of visible light. This is useful when we have cells in these bioinks or when we add nanoparticles that tend to significantly scatter the light. So here are some demo structures that we created as proof of concept. The current field of view is 16 centimeters wide at 50 micron voxels, but this is easily scalable to nearly the meter scale. And we also developed visible light active photoinitiators and identified synergetic photoinitiation when we use 2 or 3 initiator systems. And we're currently testing these hydrogel materials for cell encapsulation. One of the important aspects of light-based printing is that the shape of the layer or the part that we create is strongly dependent on the 3-dimensional light field. So in this case, we use ray tracing to be able to capture the 3D light field that is generated by the emissive diodes. And in this case, we used it to determine the optimal offset between the microdisplay and the cure plane to maximize the resolution. However, we could adopt this light field model to create a multi-physics process model, combining it together with a chemical reaction module or the mechanical property module, as well as 3D geometry. So this is more of an ongoing work. We also demonstrated the use of this technique, this visible light technique, to create multi-material structures. So here are some sample 2 material structures for proof of concept. But one of the main disadvantages of this technique for multi-material printing is that we require multiple vats. And this significantly increases the material waste as well as the cost. And it's really unfeasible for a large number of materials, for example, these tissues that we are interested in. So we had to come up with a way to eliminate the need for vats. And that is the idea behind the current effort, which is to create a hybrid droplet AMOLED visible light based system. And the novelty is that it can accommodate up to 16 different channels or materials in a high throughput manner. So as we can see in these figures, we first can deposit a thin layer containing many different kinds of ECM materials containing different kinds of cells. And this is patterned onto the AMOLED digital microdisplay. And in step 2, we can selectively and at high resolution, selectively cross-link the layer using visible light, and then we could repeat for multi-layer structures. So essentially, this creates a waste-free multi-material method that can also facilitate highly compliable hydrogels. And how do we know this? Well, thanks to a recent or ongoing work of our group together with the Van Vliet group, as part of the MIT Deshpande Center. They recently created synthetic ECM materials that had stiffnesses in the same ballpark as native brain tissue, in other words, gray or white matter. So they, using a light-based process, they created these high-resolution freestanding fibers that were just a few microns in thickness. And these are extremely difficult to create with extrusion-based methods. And so here they show that oligodendrocytes are wrapping around these fibers. So essentially they're acting as artificial axons. So this demonstrates that light-based processes find really a niche for the biofabrication of high-resolution, ultra-low stiffness materials. So using this hybrid platform, we would like to create multi-layered tissue structures that have embedded multi-scale vascular networks. And we also want to add growth factor releasing matrices. So the first step is to create these neural tissue units. These are cubic, and we have the gray matter that is essentially the matrix here. And the white matter appears as tracts, the geometry of which we can control on demand. And we also have neurovasculature embedded into these structures. This replicates the BBB, or the blood-brain barrier. So once we print a complete unit, then we could mature it in a bioreactor that is perfusible. And once these tissues have matured, we could test their activities in terms of the electrical synapses using and record them using microelectrode arrays, or MEAs. And the next step would be to further engineer these the properties of these hydrogels in terms of physical, chemical, and biological properties. So we could control the porosity by changing the molecular weight and cross-linking density. We could control the rate and the degree of swelling in these hydrogels. We could induce thermoresponsive morphing or photoreversible patterning for release, on-demand release of growth factors and other cues. And we could also functionalize these polymer networks with cell adhesion domains and so on. And we could explore use of self-healing hydrogels. So this is really, the last bit is the planned work, but we're presenting a new bioprinting approach that could create more accurate tissue models and neural microenvironments that can find a plethora of different applications. So thank you very much. And because some of this work is ongoing, we really value your feedback. Thanks again.
Kavin, thank you. I send you the virtual and the physical clap, and thank you for the presentation and for the work. Participants, please feel free to raise your hands or to type a question into chat. Let me actually ask a first question, Kavin. Yeah, I know the focus of the work is on tissue models. I was wondering if you could say a little bit about, is there also a pathway where the same technologies, if not the same materials, could be then targeted for creating graft or tissue replacements and not just having sort of ex vivo models?
Right, so the idea here is that there are existing technologies like organ on a chip or using spheroids, but really this type of bioprinting that we're presenting, that we're trying to pursue is an upgrade on those previous techniques, and it allows us to basically open doors to not just to create models, but also be able to create functional organs directly that have vasculature, that have matured, and at some point we could turn them into suturable implantations that could be used in animal testing trials, and in a long shot would be human trials. So that's the path that we're trying to pursue to create a complete method that can address many different issues and resolve these.
Mm-hmm. Thank you. There was a question texted, or not texted, but chatted directly. Yeah, I guess it's more, you mentioned some collaboration with the Despondé Center. Where do you see the near-term opportunities for translation into practice outside of the research arena, and what are those commercial opportunities, or nascent as they may be?
Yeah, so currently, as I mentioned, bioprinting itself is still a baby. It's really, there's a long way to go before it can be commercialized or used in practice. But if we think of just the platform development side, we're creating a visible light technique that is scalable. So we could create large parts that have multi-scale capability. And these could not only be useful to create bioinks or biomaterials, but also to create other types of applications. So that side, I see a lot of potential for near-term commercialization. But I would say that the bioprinting, we really have to keep pushing and see where we stand. And there are many challenges along the way. But we are hopeful that in the next 5 or 10 years, we can get amazing results. Thank you for the question.
Thank you. Participants, please ask a question directly, or send a chat, or raise your hand.
I have a question,
Teresa,
Brian, if there's not something. First of all, I'm not a scientist, so I'm sort of responding as a patient, as someone who's had a lot of medical interactions over the years. I was really excited to see your material that had a memory to reform back to its original shape. I was wondering if you'd given any thought to applying that to like supportive braces for, say, like stroke patients or other people who have neurological issues with their muscle strength. That was like an immediate like, oh, this is so exciting for me. I have a lot of these like silly little braces, right, that a lot of us have to live with, that really just hold everything still because there's nothing better. So I was curious if this is something that you think could potentially be used in this area.
Yeah, absolutely. I think there is that field of 4D printing has advanced quite well. So what I showed was just the basic deformation, but we could control. And by the way, the mechanism is really, imagine spaghetti, right? We can program it and then stretch the links, and then when we expose it to higher temperatures, these links become looser and they snap back to their original form. But there are different techniques that are reversible and programmable over a cyclic manner. In other words, we could have many cycles. So yeah, that is an active area of research, and it is being applied to the biomedical field. And really, these are so-called smart materials, right? So
I see.
Yeah, thank you for your suggestion.
Yeah, no, thank you for this work. It's really inspiring. So
thank you.
Another question chatted to me directly. If you had some number of dollars, they quoted millions here, but would you direct it to materials research or process research?
Yeah, I would say the material science part of this research is quite heavy, and these materials are not only expensive, but there are many different variables that in terms of the ECM, the extracellular matrix materials. And so, for example, here we're using visible light, which is somewhat new for bioprinting. And so these materials have to be tailored towards being active or responsive to visible light. So there are a wide range of different photoinitiators or visible light photoinitiators that need to be tested in terms of their biocompatibility, in terms of the speed of the process or the cross-linking. So I would probably spend most of the money on material development and testing, because it's all about the environment that we create for these cells. And if we could create a nice one, then the cells will behave nicely and basically do the job for us. So
very good, Kavin. Thank you for that. So I think with that, that's probably a good place to end. We'll see if we can get you those couple $1 million here from the participants, see if they're a sponsor in addition to an attendee. But Kavin, thank you for the phenomenal work and the phenomenal presentation.
Thanks for the opportunity.
Thank you.
I really appreciate it.
Our pleasure. Thank you for the time, everybody. And again, this is our way to stay engaged and to let everybody know that the wealth and diverse experiences and research that's happening on campus. I invite you to join us again next week, same time, same channel, for an external speaker, professor at MIT, but in a different department, in nuclear science and engineering. Mingda Li will be sharing his work, A Tale of Two Singularities. So this was a recommended speaker from some of our MechE faculty, and I look forward to his talk and to the attendees to please come back and spread the word. And if you, yourself, your colleagues, external partners would like to get on the mailing list, please let us know. If you would be interested in presenting, or let us know the topics that you would like to hear more about, do let us know. Send a note to MechE Alliance at MIT.edu. And with that, everybody, please stay safe. Kavin, one last thank you, and attendees, thank you for your time.
Thank you so much. Have a great day, everyone.
Thank you. Stay safe.
Thank you. Bye-bye.
Bye.